Okay. Okay, so let me share my screen. Can you all see my screen?
Yes.
Yes.
Great. Okay. Okay, yeah. So as I mentioned, this is the first lesson for the advanced topics in reinforcement learning from theory to practice. And today we'll cover basics of reinforcement learning and we'll focus a bit on exploration. So how many of you are already familiar with reinforcement learning? Actually, how many of you are not? Can you send a message in the chat and or just talk just to understand how much I should go fast on basics and how much I should not. So I don't see any message and I didn't hear anything. So I'm assuming everybody has some basic knowledge of reinforcement learning. So this will be the assumption I'll be relying on. So let's start by saying who I am. So you all know, I guess, or maybe not, who knows. My name is Roberto Capobianco. And I'm an assistant professor at the Sapienza University of Rome, but I'm also a research scientist at Sony, specifically at Sony AI. My research interests are specifically reinforcement learning, explainable AI, robot learning, knowledge representation. Here I put some images of things that I like that I'm so I'm very interested in. This is a tradition that we have in our lab to do this. And in general, in labs I belong to where people basically like to say contextualize their personality so that you can understand also a bit more who you are interacting with. This said, I think we can start. And as you all know, reinforcement learning is many things. So first of all, is a problem of interest and of studying several fields, including, but not limited to, psychology, artificial intelligence, neuroscience, and so on and so forth. In fact, there are even conferences that are for these different communities. Like, for example, there is the RLDM conference, which is the Reinforcement Learning and Decision-Making Conference, who's held not every year, but I think every other year. And in this conference, typically you can find different people from psychology, AI, and so on and so forth. Reinforcement learning is also a research field per se, so specifically belonging to the sub-area of machine learning, and currently is also quite trending research topic. And reinforcement learning is also the set of algorithms and approaches that typically are used in the community in order to solve some specific problems. So I have created the first set of slides with several videos so that you can understand a bit more the ideas, where this comes from, and why I say this is very much inspired by biology and psychology and so on and so forth. And you will also see the most recent outbreaks that reinforcement learning has been able to obtain, and researchers in reinforcement learning have been able to obtain. Now, I want to just make sure that I can share the audio as well. So let me stop sharing the screen just for a second, and I want to share the audio coming from the system. Share screen. Do you know what's the easiest way to do this? Otherwise, we can try, but I'm not sure this will be working. I'll try. But let's share the options. Okay, let's share again the screen. Let's see. So, more share sound. Okay, should work. Let's see the chat. Okay, so you should be able to also get the audio from the computer, and if not, please let me know just by interrupting me. So this is basically what happens when you do reinforcement learning. So you see there is this impala who does not know how to walk, and it basically you will see that by trying several times, you will be able to do that pretty quickly, actually. So this is a quite long video. I think we can send it faster as well. Oh, sorry. So you see, the impala is trying a few times, getting pushed by mom to do that. And now you see that after trying a few times, it was almost successful, just started to stand at least. Now it's trying again, failing several times, but eventually it will succeed. So this is a trial and error learning, and this is exactly the same thing that we do in reinforcement learning. Okay, so when I say this, I mean exactly the same, what I'm saying. So this is an example of, I don't know why there are subtitles in French. Okay. Here in this video, you will see a reinforcement learning algorithm, learning to play one of the several Atari games, specifically, this is Breakout. So at start, it's basically very bad. You see, it doesn't manage to go where the ball is. And this is during training. So now the agent is trying several times. So the agent starts with zero knowledge, like the impala, and it has to learn how to play this game. So as you see here, after 120 minutes of training, meaning trying several times, doing exactly what he was doing before, now the agent, by using a reinforcement learning algorithm, is capable of playing the game very well. So when I say the agent, I mean anything that controls this system, which is controllable, okay? So you see, after even more training here, 240 minutes, Now, the agent even learns to send the ball on the side and create a tunnel in order to break everything, which is what an expert player would do. And you might say, okay, learning to walk is quite complex compared to playing a game like this, where the controls are basically to go left, go right, and it's very simple, and you're right. But we can see that there are much more complex tasks that can be achieved by using reinforcement learning. Specifically, for this video, I will let the video talk by himself. So there will be a speaker saying what's happening. And please, if you don't get the audio again, interrupt me, because this is should be self-explained.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment, truly complex and intelligent agents will one day emerge.
Okay, so yeah, I'll not add a lot to this. You see, in this setting, we have several agents playing and doing learning in order to learn how to play. And you have seen the amazing results that have been able, that these researchers at OpenAI, which is one of the main companies working on reinforcement learning together with DeepMind and of course universities, I mean, these results are pretty amazing. Here, I'm adding another video where what I want to show you is basically that not only using these algorithms, you can learn to play video games a computer playing video game by itself, or having these virtual worlds where agents can learn to chase each other or do things that are interesting but maybe useless. In this case, we have still a useless task, but we're competing against humans directly. So again, I will let the video speak by itself, but this result is also pretty amazing because you probably all know the video game Dota. And in this video, you will see a reinforcement learning agent, actually several reinforcement learning agents, collaborating and winning against humans and achieving levels of play that are amazing. So let's start this video too.
Dota is one of the most popular and challenging competitive video games ever. Playing Dota means you have to coordinate and focus as a team of 5. Last year, we built a bot that defeated the world's best players at the 1v1 minigame. This year, we want to beat the best teams at the full game. To do this, we've built a new AI system, which we spent the last few months training. It uses reinforcement learning at a much larger scale to train our bots to play together as a team. We're now starting to play against amateur teams to test our skill. And to our surprise, so far, we've won our first games against every team we've tested.
Didn't.
What?
Yeah, but he's gonna kill you too. Someone else TP bot him.
I tried.
Everyone TP. Everyone TP. Everyone TP. Get this guy. I can't even.
But to figure out how good our bots really are, we asked a Dota expert to take a look.
My name is William Lee, better known in the Dota community as Blitz.
Blitz here with Chrissy. Just going to give a brief explanation of the game for people that don't know about the game. Rules are very simple. It's kill the enemy team, take the buildings. Every hero has a variety of unique spells. They'll be playing a mirror mode where both teams have the exact same heroes.
Here, the human team is dealing significant damage to the baseless 5, and Crystal Maiden comes in to defend the barracks. She jumps in with Blink Dagger and shields herself with Black Cane Bar while channeling Freezing Field to deal massive amounts of damage while being uninterruptible. Due to her combo, she ends up taking out 4 human players in a 2v5 fight.
Oh, wow.
Yeah.
Well, that's it.
Oh man.
GG.
And GG's called. Good game. Humans no longer think they can win. They would be absolutely correct.
So their dev team got absolutely crushed. I think it was the fastest casting gig of my life. Then it went into game number 2. The humans kind of, they had time to like think about the game and stuff like that. They got crushed even harder.
And the bots did exactly what I hoped for, is they own this area of the map. You take away 2/3 of the map. They didn't even touch these 2 bottom towers, and they would be 100% correct in this. This is like one of the highest level plays that you can make. This side of the map is incredibly hard for the bots to control, and so they're just playing this top side and this mid side because they understand that these are the 2 most important parts to control in the game. The ability to like intuitively do this is insane. Doing it one game, I could maybe chalk it up to just dumb luck. Doing it 2 games in a row, flipping the sides, means that it's more than just coincidence.
It took me, and I'm fairly reasonably good at the game, 8 years before I learned some of the strategies. I would say it was pretty easy to quantify for me. It was about 8 years for me to learn the strategies that the bot was intuitively doing.
To train our bots, we use reinforcement learning with self-play. We run the game on over 100,000 CPUs, and our bots learn from every game they play. Because Dota is so complex to learn, even for a single player, we created a hyperparameter, which we call Team Spirit. The 5 bots start out completely selfish, but tuning this knob tells them to care about their teammates so that they can learn to play together as one unit. After seeing the bots win against the test team, Blitz wanted to challenge it himself. He has a higher rating than the test team, and we paired him up with the best players in our audience.
And so we can see Blitz is about to die here.
Blitz is.
So I think we can pause the video here. What I want to say regarding this video is that you see that these players in the bot team are collaborating to win against the enemy and against the humans. And the very fascinating thing is that each of these agents is trained by as an individual. So it's not trained using any centralized algorithm that basically shares information between the different agents. But each of these agents learns independently. So this is very fascinating and interesting. Okay. And last but not least, we started with the Impala learning to walk. And I want to show you that basically in simulation with these simulated robots, that, I mean, they're much more simple than robots, of course, but in simulation, you will see that these agents that do not know at all how to walk will learn to walk by just interacting with the surrounding environment. And basically will be the environment itself generating some behaviors that can even look funny to us, but they are actually useful for the agent itself. So let's start this video too. So here the agent is learning to, as you see, run, jump, do everything it needs to do by just receiving sensory information about the joints and learning about how to control each of the joints. So it's doing very low level control. So there is no prior knowledge, as it's written in the top of this video, and there is just the reward, which is going forward. So the reward is basically what kind of signal the agent is receiving. So how does it know if it is doing well or not? And you see that this algorithm can be used on different embodiments for the agent, so in different structures of the robots, let's say. Even humanoid. And as you see, it learns this funny way of walking because it gets momentum basically from using the arms. Okay, so we don't have to see everything of this video, except that you might want to see that at the end, the agent is capable of learning to run pretty well. Okay, so after all these introductory videos, we can probably start formalizing a bit the problem. And the way we formalize a reinforcement learning problem is by means of something that is not specific to reinforcement learning, which is the Markov decision process. So the Markov decision process is nothing else than what you see in this schema, where you have an environment and an agent. So the agent has to act in this environment by means of some actions, of course, and the environment returns to the agent an observation, which corresponds to the state, because we assume that the environment is one-step Markovian, so we don't need any memory, and typically we also assume full observability, so otherwise there are partially observable Markov decision processes. And in addition to the state, so the observation, the agent receives also a reward. So a reward is an instantaneous numeric signal saying how well the agent is doing by selecting a certain action in a certain state. So I don't know, if the agent jumps and it falls in a pit, then it gets -100 reward because it's dying. Otherwise, if it jumps, I don't know, it catches a ball, then it gets +100 reward, for example. So again, here there is a small dictionary of what we have in an MDP. We have an agent, which is the entity interacting with the word, like, for example, it could be a robot, but it can be any virtual agent, like the pad of the breakout game, or the hiders or the seekers in the game that we have seen, in the video that we have seen, and so on and so forth. Typically, we assume that the environment in the agent operates in a time discrete setting, so where the agent basically selects an action at time step t, and at time step t plus 1, the state that the agent observes is a new state, based on which the agent selects an action at time t plus 1. So at every time step SSA, the agent receives a reward and a state, which is the observation. And the environment, we get a new observation because the environment transitions in a new state by means of the action selected in the previous state. So there are environment transitions that are often actually typically non-deterministic. So there is a probability of transitioning a certain state as t plus 1 given the previous state as t and the action selected at time t. In reinforcement learning, as we will see, this transition function is not known to the agent typically, but in MDP, the MDT is modeled by means of this transition function. Environments, or actually the tasks that the agent has to execute in this environment, can be episodic or not. And this is relevant because in addition to, if the task is episodic, in addition to state and reward, at every time step, the agent also receives a Boolean flag, basically saying whether the task has been completed or not. So it's a done flag. It's called like this. So this is an example MDP where basically you can see transition between different states and rewards. So if you wake up and you go watching Netflix the whole day, and you can basically continue only watching Netflix because you will not do anything else, you get -2 reward at every time step. Otherwise, if you go to do, for example, coding and debug, you get instantaneous -3 because it's frustrating for you, but in the end you will succeed and you will be able to deploy your code, so you get a positive reward for yourself because you're not frustrated anymore. You are actually satisfied of what you did. And as you already see here, in order to get some positive reward in the end, the agent has to go through this state where it receives a worse reward compared to the one in this state, but eventually can transition to the deploy state, which is or also to the sleep state, which is positive for the agent. So I already gave you some intuition of what, but you already are familiar with reinforcement learning mostly. But so just to repeat, there is a notion of not being eager to just receive good rewards in this present state, but you want to look at the future and plan basically in your mind regarding how and what kind of actions you should execute in order to get accumulated a summed reward which is the best as possible. In fact, solving a Markov decision problem typically implies finding the optimal policy by star. So a policy is a mapping from all the states to actions. And so basically you can have two kinds of policies, which are one which is stochastic policy and another one which is a deterministic policy. Stochastic policy basically defines the probability distribution of your actions, and actions are then sampled from this probability distribution. So here I mentioned the term policy, which is the one that I have just described, and optimality instead is defined in terms of value. And the value of a state is exactly what I was mentioning before. So the value of a state, which depends on the policy that the agent is following, is defined as the expected sum of discounted rewards obtained by starting from the state S and following the policy pi. So why does it depend on the policy? Because of course, if you have a policy that never selects some action, then the value of a certain state will have to be, for estimating the value of a certain state, you will have to take into account that you will never go, for example, looking at this MDP. If the policy always says go and watch Netflix, then you will never visit this state. So your value will never have to consider the fact that you might end up in the deploy state or in the sleep state. So an optimal policy in the end is the policy that maximizes the value for all the states. Okay, so it's the argmax of the value of the state multiplying here the probability of transitioning in that state. So here there should be an S prime. That we're good. Okay, so here we are assuming that we know the transition probability, which is, as I said, typically not known. But in case you know the transition probabilities, then you can apply the Bellman equation. Things are easy because you can use this equation in order to compute the value of a certain state based on the value of the neighboring states. Here, let's assume a state as a cell in this grid for easiness of thinking, but it doesn't have to be like this. But for you to understand better this concept, you can think that the value of this state will depend on the value of this state and of this state, right? Because if you know the value of this, basically one step that you need to estimate. So, and this is exactly what the Bellman equation does. So it considers the reward that you receive in that state that you're in, and then considers the action that leads to the maximum value state. And there are two algorithms that you can use to solve the MDP by knowing the transition probability. These algorithms basically perform dynamic programming, and these are known as value iteration and policy iteration. As you see here in the value iteration algorithm, basically we are directly solving the Bellman equation, but just in an iterative way. So you do, you start with some values that are arbitrary, like for example, you say that every state has 0 value. And from this, you basically just start collecting that you get in every state. So for every state that belongs to the state space of the Markov decision problem, then you look at what is the reward, and you use that to estimate the value of that state. Then at the second step, you will have an estimate of neighboring values, right? Because you will be collecting in the value of the next state, of the neighboring state, the reward that you get there. And so you can update your value for the current state by taking that into account. And if you could keep iterating, basically you can keep into account everything which is in the state space. Of course, in order to do this, you need to know this transition probability. A similar concept is for policy iteration, except that in policy iteration, you take into account what is the action selection of the policy instead of selecting the action that is the action that leads you to the maximum value state. So this is what changes in this step, and in this other step, you just try to change your policy based on the information that you collected. I don't want to focus too much on these topics because this is just a very small recap of what's here. If you need, I mean, the slides will be shared, and if you need any other pointer, if you're not familiar with the topic, you can just send me an email or write on Classroom, and I will share the material, additional material with you on that. Now we have a problem. As you see here, we're using a value function, which tells us what is the value of a certain state. But if we don't know the transition probability, we don't know which action leads in which state. So that's why we typically introduce something which is slightly different, which is the action state value function, where basically you are not only saying what is the expected value of the the expected sum of discounted rewards obtained from starting from that state, but also you take into account a certain action. So now we are considering what is the expected sum of discounted rewards obtained starting from this state and taking this action, and then after that following the policy pi. So there is a relation between the value function and the action state value function, which is that the B is the maximum, basically the maximum action over Q. So the action that leads to the maximum action state value. Now, why do we prefer Q compared to B? It's very easy, because if we can do an argmax over Q in order to know which is the action that is maximizing the value function. And so we can directly compute a policy from Q without knowing what is the transition function. And this is why in reinforcement learning, where, as I already said, we don't know the transition function, we typically prefer to use Q compared to B. Now, the title of this slide is very clear, from planning to learning, because if we assume that we don't know this transition function, then we can do very simple things with this equation and basically convert this thing to an expectation, because we know that Q, as I said, is an expectation over the value of the over the sum of the discounted rewards that you would get from this state and taking this action, then following the policy. But it's an expectation. So this means that if you're doing sampling, then you can just do your sampling and you can sort of update your Q function in an iterative way, and still this equation holds in expectation. So this is doing sort of deterministic, in a deterministic way, what this other equation is doing in expectation, except that this and you will see that basically this equation, for this second equation, if you are at the fixed point, they should match exactly, except this expectation term that I was mentioned. So if you're doing this, you're basically already performing reinforcement learning, because this is the equation of one of the most famous algorithms and most simple algorithms in reinforcement learning, which is Q-learning. So you see that this is exactly the Bellman equation, except that you're not using the transition function, but you're assuming that you're sampling from the environment and using this information in an iterative way. In order to assume this, however, there is a catch. If we're doing sampling and we say that Q represents an expectation, then we need to visit enough states in the world in order to say that this Q estimated using this formula matches this. So we need to be sure that we visit all the states, all the next states, or if not all, as many as possible states, in order to have an accurate estimate of Q. So this leads to a problem, which is the exploration problem, which is one of the main focus of this lesson of today. So we need to explore. Exploration means that even if we have some knowledge, so which is our knowledge currently is represented by the Q function, which tells us how good a certain action and certain state are. We need to, and this is, if we use this information, we are exploiting the Q function and selecting the action that leads us to the best Q, estimated Q function, so the best value, which is basically allowing us to solve the MDP. But on the other hand, sometimes we need to explore. So we need to take some actions that we don't necessarily know whether are good or not, because this allows us to basically try new things, visit new states, and acquire new knowledge, which can be embedded in the Q function itself. So if we go back to our example over here, if we have a policy that basically tells the Q function tells the agent that in this state, the action with the maximum value is NAP, right? So this is because our current estimate is like this. So this is what we estimated, or maybe we have injected this prior knowledge in our Q function, and we say, okay, this is what you should do. So if we just exploit, the agent will always ever continue to do NAP, wake up, go code and debug, and NAP and again. So the sum of the discounted, the sum of the accumulated rewards will be always, decreasing, because this here we have a -3, which is the highest, the smallest value that we get, which is dominating. But if we try one time, instead of following exactly the Q function, we try one time a different action, which is going and do deploy, then the Q function can get the information, which is if we go here, we get a different reward, which is better. And after that, we can go to sleep, which is even better because we can accumulate another positive signal. And so this is very important. So now when I was talking, I just noticed that I said several times the expected sum of discounted rewards. I didn't introduce this term. So discount, the discount factor is this gamma that you see in these formulas. And this is just saying us how important the future is. So if the discount factor is 0, you see, for us, it's only important the reward, because this term regarding the future, the neighboring states, we don't care about. But if this is 1, then we basically the rewards that you get from next states are as important as the one that you get in the current state. So this discount factor is basically telling us how much we should care about the future actions that we need to take into account. So typically when you do reinforcement learning or planning via dynamic programming, this is set to a value which is higher than 0, of course. Otherwise, you are only considering the present, not considering the next states. Okay, so as I said, this switch from planning to learning happens in a pretty straightforward way by just assuming that we don't know the transition function and acquiring information in this online fashion. This introduces us to the Q-learning algorithm, and the Q-learning algorithm allows us to learn the optimal policy using off-policy data. So off-policy means that data is typically collected using a different policy compared to the one that we're learning about. And on-policy instead means that the data is collected using the same policy that you're learning about. Now, why is the Q-learning algorithm of policy? Because, as I said, we're learning about the optimal policy. And why are we learning about the optimal policy? Because we're selecting as you see here, we're selecting the action that leads to the maximum value in the state S prime. So this means that you want to select the best possible action. But while we collect our data, we are of course not doing that. And we are even acting in a epsilon greedy way. As I said, epsilon greedy means that sometimes you select some random action. So we're definitely not following an optimal policy, but still we're learning about the optimal policy. In Q-learning, you could even collect your data by being completely random, so by executing a completely random policy that executes random actions without any sense, basically, and still you would be able to collect information about what is the optimal policy and learn about it. There are a few concepts that are introduced by looking at Q-learning. That is the fact that in Q-learning, we typically use this notion of bootstrapping because we are computing our value based on a previous estimate of the value itself, which is wrong, but still we're building on that, assuming that this is efficient enough for us to build a better estimate. At the same time, we are introducing what's called the temporal difference error. So now we're using the naming of reinforcement learning, which is nothing else than what's already happening in the Bellman equation, except that here we are defining it in terms of an explicit error, where we basically say, okay, what is that I was considering to be the value of it that I'm in, and what is that I see is the reward that I got now. So the signal, the actual signal that I'm getting, plus what I'm in the future. So there is what this error that takes into account the reward that we get in this step, this single step, that defines the error from our previous estimate to the actual signal that we get. Now, if you want to be on policy, the switch from Q-learning to an on-policy algorithm is very simple. We just need to remove the maximum over the actions here, and we can select an action instead based on our policy. And you will see that if we do this, we are changing nothing else than this term over here, and we are going to a completely different algorithm, which is SARSA. As I said, it belongs to a different category because it's non-policy. Here we are considering explicitly the action selection of the policy in order to build our estimate. And based on that, we can see that Q-learning learns the optimal policy, while SARSA, that is executing an epsilon greedy policy, takes into account the fact that by being epsilon greedy, sometimes the agent can fall in the cliff. So, which is definitely not good for the agent. So it doesn't learn that policy because it's a dangerous policy. Okay, of course, if you have any questions or things you're not understanding, you can interrupt me anytime. And I said we switched from this algorithm Q-learning to SARSA by just changing this term. And this is true basically for every value-based method. So every method in reinforcement learning that relies on an estimate of the value function to define also what is the policy relies on this formula where we have a target. So we are updating our previous estimate based on the error between the target and our previous estimate. So the Q-learning target is the one that we have just seen. The SARSA target is the one that doesn't take into account the maximum, so the best action, but the action selected by the policy. Then we have other algorithms like expected SARSA, which takes into account the probability distribution of the policy, or a Monte Carlo target, which takes into account the average return, where the return is the sum of the discounted rewards that you get at the end from a certain state to the end of the episode. So when you get the done flag to true. And yeah, so that what you're changing here is just this target, and you can apply the same formula for every and each of these algorithms by changing just this term here over here. Now, all of this is quite nice, but if you look at this image over here, you will notice that, and also if you just consider what we just did, we said we need to compute the value for each state and each action, and this is very bad. So forget the term deep here, Q-learning. You see, if you have a very large state and action space, then you see, please wait, I have still 20,000 actions to calculate their Q values before giving you the best action to take. If you take a different approach instead, where you directly estimate the policy, like policy graded methods, you can directly get the action to execute. So typically in policy graded methods, instead of estimating a value function, you still estimate some value function, but instead of using that in order to define your policy, you directly represent a policy by means of some parameters. So you create a parameterized policy, and you define a performance function, which is basically what the performance term is the value function itself. And then the policy gradient theorem, which I'll not go through here, but again, I can send you material if you need to, and you're curious about this, tells us how can we compute this gradient for this performance function and change the parameters of our policy. So this is the way we do this. We don't need to go through this formula, but the idea is that given the parameter space and given the cost function, which is in this case a performance function, the policy will perform several steps of improvement towards the parameters that allow us to receive the best performance and so receive the best value in that state. Okay, so this is an overall idea of what happens there. And actor-critic methods are basically an intermediate between value-based methods and policy-graded methods, where we still have temporal difference methods that are temporal difference methods like Q-learning or SARSA that are used in order to estimate the value function. But then this value function is directly used to improve at every time step the policy itself. So this is basically really temporal difference methods meet policy graded methods, because this is what exactly happens. So you have the policy, the actor, so that which is called the actor, and the critic, the value function. So the reward is used to update the value function. The value function is directly the thing that is used to improve the actor. And all most recent algorithms at the state of the art are typically actor-critic methods, except very few of them, like deep Q-learning. But again, it's one of the previous algorithms of this trending topic of deep reinforcement learning. And here instead we have deep deterministic policy gradient, soft actor-critic, proximal policy optimization, all these algorithms over here that are the ones, again, there are reference papers for all of them if you're curious about this, but we'll touch everything also in the next lessons. Few other things to say. Of course, when I say that you learn the value of a certain state, or you learn a policy, you can do that by doing either tabular computations, meaning that you have a hash map or something like that, a table where you store the values for each state and each action. Or you can do a function approximator with a function approximation, which is what you do when you use, for example, a neural network, in order to approximate the value of a certain state or the policy, the action that you should execute in a certain state. And in both cases, you don't want to necessarily deal with the state that the environment is providing you, but you want to maybe construct some better or more structured information on top of the state. And typically this is what you do with featureization, which is again used both in tabular and function approximation land. And you can have different ways of featureizing your state. So creating features out of your state, which is, for example, polynomials. This is never used. It's a very, unless you're doing very easy things. Fourier basis, coarse coding, where basically you have these circles that are built on top of your states, and then you're saying you're creating a set of booleans, 1 and 0s, whether your state falls in one of these circles. And depending on how close and on the shape of your circles, you can allow generalization between states, because you see, basically in this state, you have 3 circles that are at 1 and all the other ones are at 0. But instead, if you have these more intersection between these circles, you see that more circles turn gray, so they are at 1 when you are in a certain state. And a similar thing is...
I have a question.
Sure, yes.
About the circles, like, do you have to choose their shape, or are you using some kind of function to shape them accordingly?
So in the most traditional way, you can just define the shape and the structure and the distance of your circles. This is what you typically do, but there are also approaches where you can sort of learn and optimize these all together. Consider, however, that in, as I was going to say in next slides, at the state of the art, very often you have neural networks that directly work with the raw state, so the unprocessed state, because they perform the featureization for you. But in any case, if you use these circles, you define the shape, you define the distance. Okay, and also the number of circles that you want.
Okay.
And similar thing is for the tiling, which is the same idea of these circles, except that you are now creating overlapping grids, and you are saying, now my state falls in this square or not. Why do we use squares instead of circles? Just because they are much more efficient to compute. So that's the only reason. And you can do this, and otherwise a very similar concept, although different in its nature, is the notion of using radial basis functions, RBFs, which is basically defined by using, instead of circles, Gaussians. Okay. And as I said, in most recent approaches, you can, instead of using featureizations like this, you can use some either pre-trained neural network or a network that you train yourself in order to produce an encoding of your state. And I'm saying this because this is something that it will be actually relevant for the next slides regarding exploration. So there will be one approach where people have used exactly this in order to improve exploration, but we'll see. So when you will get the slides, you will also receive these links where I provided an implementation of Q-learning with tile coding, which is the one with squares over here. So this is the tile coding, this is the coarse coding. And so there is an implementation of Q-learning in tabular way, also Q-learning with a neural network. Now, unfortunately, this example I created quite some time ago, so this is still in TensorFlow 1. I want to port that soon in TensorFlow 2 or PyTorch, but this is still, you should be able to get the idea out of it. So you can understand how easy it is to switch from a tabular approach to one using neural networks, because yeah, it's just really creating a loss function that's doing exactly the same thing that you do in tabular way. And I don't think we should spend too much time on this code. However, now, at least if you don't have questions regarding this next time, or I mean, if you have questions regarding this next time, we can talk about it. But I think for now, we should just move on and continue and give you the time to look at it and get any questions if you have them. Now, this is a bit, I don't know why it's so bad, but yeah, it wasn't so bad yesterday when I was editing the slide. Anyway, so now we are starting our escalation from the basic knowledge of reinforcement learning that we just got in a very quick way to something which is much more complex and interesting. So DeepQN, Deep Q-learning, is basically the first approach that has been able to win and actually achieve superhuman performance in several Atari video games. So Atari video games are like Breakout, Space Invaders, many other. But these video games where humans were, of course, very good at, DeepQN was the first algorithm capable of achieving superhuman performance at many of these games, not all. And now you would say, okay, so it must be something exceptional, very difficult algorithm, something amazing. Actually, it's not anything that you couldn't learn in this 1 hour before, because it's Q-learning with few tricks and the use of a neural network. So the few tricks are the fact that instead of using directly the information that you collect from the environment, so the transition, instead of using directly the reward signal that you get from the environment when you get it from the environment, you store it in a database, in a data set, which is called experience replay, and where you say, okay, I have seen this transition where by taking this action in this state, I got this new state and this reward. And you store it in this data set. And then you sample some mini batches of this information from your data set every once in a while, and you use this to update your value function, action value function. And how do you update your action value function? Exactly by doing Q-learning and by using a neural network. So exactly the code that you see in this slide, except that with an experience replay. So nothing amazing, very simple, still achieved very important results. Now, this started in 2015 and led to, after 5 years, to Agent 57, which is the agent that is the first approach capable of beating humans in all Atari games. All Atari games means also the most complex ones. And there are few of them which are very complex. So now we'll go not through all this timeline, but we'll visit some specific parts of this timeline where important improvements have been obtained. But let's look first at what I mean that not all video games are as easy as Breakout, and not in all of these video games DeepQN was capable of learning. So as you see, there are few of these games where the agent is obtaining very bad performance, and specifically Montezuma's Revenge is the most terrible one, because basically the agent is even getting 0% performance. And so you will understand by looking at this video why, if you're not familiar with this video.
So going back to the graph, when I was presenting this paper to my class, I noticed that Montezuma's Revenge, it was just a 0. So another one that's interesting is Pac-Man's pretty low. But let's look at Montezuma and why this sort of learning system doesn't really ever make any progress at all. So I downloaded the game, and let's play it. So as you see, I'm walking with this guy. I'm controlling him with the up and down arrows, make him jump with the space. And I'm supposed to get him over to the key. So, you know, I think pretty quickly you sort of figure out that the idea is to take the guy around the corner, jump over this guy. Oh, didn't work out that time. And, you know, if you try to just jump this way, you can't quite make it. So, you know, fairly sophisticated game, but not so much. Anyway, I got up. I got the key. Now, the problem with that game is there's no reward until I get the key. So let's take a look at, you know, an agent playing this game, what that might look like.
So when this person says there is no reward, we mean that there is the reward is 0 always, except when we get the key. So there is no signal.
You know, the good news is, you know, it experiences the environment, see it's going to fall down. You know, that's a 0. You know, he sort of knows that he died, and you can see that even a mostly random agent eventually figures out, you know, he's able to have a session where he gets all the way around and takes the pull and goes down. Well, this guy's not doing great. Let's see, come on. Yeah, there he goes. Awesome. So you see that happens, but the problem is a human can tell that we made progress. We got closer to the key. that we're getting, near here by going all the way around. But the rewards are still 0. So, I'd love to see what, the agent for DeepMind looks like, but for all of their machine power and all of the work, they never make any progress. They never actually get to the key because their algorithm is based on sort of doing nothing, adjusting the epsilon, and learning and doing levels of learning and seeing which actions lead to higher reward. Now, here I can imagine making progress by designing some sort of intermediate reward. Like, if you see the game, you can say, okay, well, maybe going further and not dying is a reward, and what can you do that way? Not as big a reward as getting the key, but, sort of something. But without that, you just can't get anywhere. So it would almost be like playing chess or Go, and the only reward being whether you won the game at the end is a 1 or 0. It's just, maybe you could adjust some of the parameters and you can get that far, but I'm not even sure it's possible with just random actions to get all the way to the end and to learn sort of how we got there. Although maybe it is, because here I just have random actions, and this guy hasn't gotten to the key yet, but he's come pretty close. So anyway, that's all I wanted to show you guys. In fact, the intermediate rewards is something that's pretty interesting and something I was...
Okay, so you got the idea. The agent doesn't see any reward at all until it gets to the key. And this is basically not allowing the agent to learn anything. So this is an exploration problem, because even if the agent tries some random actions, it doesn't see ever any good signal, anything that's relevant for it. So it doesn't know how to improve its cumulative reward obtained over time, because it doesn't ever see that information. So going random, as we said before, is not sufficient in this case. And
going back to the...
okay. So there are few methods that exist in literature in order to promote exploration. And the easiest one, although the less relevant for us at this point, is the one of using entropy. So if you add an extra entropy term in the loss that you used in order to train your policy, then you're basically allowing your policy to be less committed, and you encourage diversity between actions that the policy can select. So basically, you're saying to the agent, do not commit too much to following some actions. But still, even if you do something like this in Montezuma's Revenge, this is totally useless. So why did I mention this entropy term? Because this is actually something that is quite common in most of state-of-the-art algorithms. For example, if you look at soft actor critic, which is one of the most used algorithms nowadays for standard reinforcement learning problems, let's say, typically you will see that there is this entropy term which is used. So this is there. Still, this is absolutely not enough for something like Montezuma's Revenge. So now we get to something completely different, which is count-based exploration. So instead of going random, and entropy is still considering basically the random aspect of our policy, we now inject some prior knowledge in this exploration methodology. So the easiest idea that you could come up with is the following. So you count the number of times each state is visited. And based on that, you add an extra term to the reward. So you don't have anymore only the reward coming from the environment, but there is also an intrinsic reward that the agent has internally, which is added to the reward coming from the environment. So the full reward will be now computed as the reward coming from the environment, so the extrinsic one, plus the intrinsic one. And based on this idea, then we can add an intrinsic reward to the extrinsic one, which is higher for low count states, meaning that if I'm visiting a state where I have never been, or I have been a few times, then I get a higher reward. So this is basically promoting exploration, right? Because if I visit new states, I get a higher reward. So I would want to try to visit new states. Now, this assumes that you can count the states and you can do counting on states. So there is some problem with this. So first of all, the state space needs to be limited, and you need to be able to do counting. So you need to be able to discretize your states and so on and so forth. So this is not ideal. So this count needs to be approximated. And this is basically what people have been doing in this paper, which is from 2016. Where basically the title should be pretty explicit because it's unifying count-based exploration and intrinsic motivation. And they do that exactly on our friend Montezuma's Revenge, where they try to use these approximated counts where there is some math behind that I don't think we should go through here, but you should get the idea. Again, I think the purpose of these lessons should be get all the ideas that are behind this, and then if you're interested as PhD students, you should go read the paper and collect the information that you are interested in. So I'm giving you all the pointers. So here there is the title of the paper. Here there is a link to a GitHub repository where there is one implementation of this paper. So actually, this is not the code coming from the authors of the paper, but there is one implementation of these algorithms in this repository. But let's look at the video again so that you get the idea. So as you see, one level, 24 rooms, DeepQN is capable of using just 2 rooms. Now, by using this novelty-based reward that we just talked about, the idea is the one that I said before, counting, except that now we're doing approximated counting. Now the agent is capable of trying new things. And it's even interesting in exploring transition between different rooms, as you see. It's quite funny to look at. And you see, it tries very dumb things, but it's new, so why not? And as you see, it's allowing the agent to do things that it was not capable of doing anyway. So it goes to the next. So after 100 million frames, so it's a lot of training, of course. You don't get these results with few training, but a lot of training. But still, the agent is capable of behaving much better than by looking at the behavior of just DeepQN. So it still dies sometimes, but visits much more. Not bad. So compared to exploring only 2 rooms, the agent is now capable of exploring 15 rooms, which is a significant step forward. And this is just at the beginning of investigations on how to deal with this problem. So now let's move on. And in addition to doing what we just said, which is counting, we can now think of something slightly different, which is in the idea, it's very similar, except that the principle of implementation is quite different. So the idea here is, instead of counting, if the agent sees a state enough times, then it should be capable of predicting that, right? So if we train a model in order to predict what is the next state, and we get an accurate prediction, then the state is not novel. The state the agent is going to, then that state would be not novel because it's capable of predicting that. So it means that it has seen that few times. But if the agent is not capable of predicting what the next state is, it means it's new. And then we can provide some higher reward to tell the agent, go and see, check what this state is. Differently from counting, you could say, now this is the same as counting now. The answer is not exactly, because given that we're using this approximated model, we're now not only doing counting, but we are also generalizing between similar states. So even if I didn't fall exactly in that state, or an approximation of this counting, if I have seen something similar previously, I already know how to act, and I don't need to spend a lot of time doing that thing because I've seen something similar. So I don't know, if I'm changing room in Montezuma, for example, even if I'm not going exactly to the same room as I was going before, it's still changing room. So I can generalize the fact that if I'm changing room, I don't need to do this several times. It's not something as novel as it could be something else. So this is the principle behind that. And again, I have the title of the paper here. This is the official implementation of the paper. And here there is a video from the authors of the paper itself. So just to say one thing before we continue with the video. So there are this video is on Super Mario. This approach has been used also on Montezuma's Revenge. And the interesting thing about the video on Mario is that the agent doesn't get any reward at all, except the intrinsic reward. So the reward that the agent is deciding it should get by himself by looking at how well it can predict the next state. And you can see very easily that there are some patterns here in Super Mario, for example, where you have these pipes to jump on and stuff like that, and these monsters and things like this, where they're repeating, so they're not so novel. And if the agent is capable of predicting what happens there, then it shouldn't be explored too much. So again, we'll start the video. It's Doom, which is another environment where agents are trained often. And again, also in this environment, the agent doesn't get any extrinsic reward, but only intrinsic rewards. Okay, so this was another step forward in understanding how to deal with exploration. So instead of now create approximation of counting, we are letting the network say how good it is at predicting the next state, and based on that, we can compute our intrinsic reward. Another approach that was adopted basically around the same time was that of using Thompson sampling. So Thompson sampling is basically choosing the action that maximizes the expected reward with respect to a randomly drawn belief. So this means that you can have different beliefs, and based on that, you have different predictions for the action. And based on that, you have also different predictions what is the expected reward. So you choose one of them, and you then choose the action that maximizes one of these sampled beliefs. So a belief for us in this space can be represented by a value function implemented via a neural network. So this is why in this paper that I have mentioned here, for which unfortunately I didn't find an implementation, but I think if we search better, there will be it will be possible to find one. Here there is the idea of training k different heads for the network, each representing a value function, and each on a different subset of data. So each of these heads of the neural network will be one of our different beliefs. And there is this shared part of the network just to share the representation. So this is exactly what I was mentioning before. If you use a neural network, then you can basically get a featureization out of it directly. So this shared part of the network is exactly creating a featureization for these different heads to work on. Okay, so it's trained by having shared weights between all of them, just because we want to create a common representation, a common featureization that is trained as fast as possible using as much data as we can. And here we have the pseudocode, which is again very simple. You just basically are training these different heads on different subsets of data. And in the end, when you have to execute your policy outside training, you use an ensemble network, which is basically a voting mechanism. It's an ensemble policy, where you have these different heads voting each for one action, and then the action which gets the most votes from the different neural network heads is the one which is selected. Now you could ask me, why does this promote exploration? Well, very easily, because the fact that each network is trained on fewer data basically allows us to be less committed to some previous experiences. So each head will be doing different random things, let's say, at the beginning, and different explorations at the same time, because each one will have its own belief, which none of them will be the correct one, although all together will produce some relevant information for us. So also here there is the video from the authors. And this is a paper from DeepMind again. Well, okay, so let me go faster on this part. So this is what we have already seen. This is actually a short presentation, a 2-minute presentation, a spotlight presentation they gave the conference where this paper was published. So here they're doing some introduction to exploration. And then here we are finally to what we just talked about. Each network has different heads, each of them representing a Q function. And now we'll see what happens here. I'll go to normal speed now. Okay, so this is how it learns to play. And this is the exploration part in training. So you see each network is playing basically a different version of this game. Each network head is playing a different version of this game, actually the same game, but still with its own beliefs. And they collect data and are trained in this way. So you can also visualize uncertainty in the ensemble policy that you get at the end, because if many heads vote for different network, then there is a higher uncertainty compared to the one that you get if all the actions, if all the heads vote for the same action. So for example, here, you see here in this case, there is a lot of uncertainty. Different heads are voting left, other for right. Okay. Okay, so 1.5 years after all of this, people continued studying how to solve basically Montezuma's revenge, but in general exploration. And these people here came out with this paper, for which there is the official implementation again, random network distillation, where basically they relied on the fact that a neural network can be used to provide some featureization. So they they used two networks. One is the target network, which is fixed, never gets trained. So it has some random weights at the beginning, the one that you initialize the network with, it's never trained. And given that this is fixed, it's used to create a feature representation for every state. So you say, I have this random network, I pass my state through this network, and I get some output of the dimensionality that I want, which this represents the features that I will use. And a prediction network now that is trying to predict the target network's output. So this is trying to learn what this initial target network has. Basically, it's trying to learn what are the weights of this target network. And this is used, the error in the prediction is used to compute what is the intrinsic reward that you should provide to the agent. Now, the idea is very similar to the one of predicting next state, except that instead of predicting the next state, now we are trying to predict a featureized version of it, which is definitely easier for the network to learn. So again, here we have an observation. This is the schema of the whole algorithm. Here we have an observation that we get from the environment. Our policy selects an action, and which is returned to the environment. The environment returns also a new observation. From this observation, we compute the features using the target network, and the predictor network computes what would be the basically the expected features from this new observation. And this is used to compute the the intrinsic reward. And based on that, then we can update our policy and our value functions, whatever we are using. Okay, so basically, the larger the difference between these two things, meaning that the predictor network doesn't know how to predict the target network featureization, then the larger the reward. So this means that the network promotes exploration of new states that are exactly as the other approach, except that now we are using an output of a target network. And this is called distillation, because typically predicting the output of a neural network for a neural network is much more simple than training from the data, that the raw data. So this is the reason for which they do this. Again, the idea is very simple, very much related to the paper that we saw before, except that now we're using this distillation approach. And here is the video for that. Okay. So as you see, we are building on top of things that we have already seen. And this is basically one of the papers that led to Agent 57, which is the Never Give Up paper. And this relies and builds on RNND, which is the random network distillation paper that we have just seen. And it adds on top of that an episodic memory. So we still have RND here, which generates our intrinsic reward. But we also have this extra part of where we pass our current state through this embedding network that again is creating another featureization for us. And based on that, we are then looking at this episodic memory. So every time we pass these states through the embedding network, a state is added to the episodic memory. And at the same time, the state is compared to the ones that are already in the episodic memory. And the k nearest neighbors are taken into account, and these are used to compute this multiplier for the intrinsic reward. So basically, the idea here is that if the states that we are visiting now are similar to the ones that are in the episodic memory, then this R&D reward should be not so high. But if the information, the state that we're visiting is different, very different from the ones that we have already visited that are already stored in this episodic memory, then this is something very important for us. So we should weight this reward much more, so give it a much higher multiplication factor and use this information in a much stronger way. And this is the idea of this paper, that basically, for which I don't have a video, but that led to Agent 57. Again, you will see when you will go through this paper, if you will want to do that, that all these papers have been building one on top of the other. And I think this from this outline that we have, this timeline that we have over here, this is pretty clear. So all this exploration, starting from DeepQN, this is the basics from which we started. Then adding the episodic memory and adding this exploration using intrinsic motivation, curiosity, distillation, and so on and so forth, led to Agent Never Give Up, and finally to Agent 57. So I didn't put anything on Agent 57 per se, just because there are some additional things that you will not talk about here. But the idea here is that you have also a meta controller that is switching between different controllers in a learned way. Yeah, so I mean, I think for today this is enough, and I want to leave some space for questions if there are any. Otherwise, I think we can close here for today. And yeah, any question? If you can unmute and ask questions, or otherwise I can check the chat. Okay, if there are no questions, then yeah, okay, Riccardo.
I have one bureaucratic question.
Okay, sure.
For the presence, we have to fill a form, or it's just
for the presence? Maybe no, I think it's sufficient for me taking note of that. Let me just do that in a second. Okay. Yeah, okay. I didn't know there was this requirement for taking note of that, but sure, I will do this.
Maybe it's not even necessary. It depends.
No, I mean, for me, it's not important in the sense that also I'm recording on YouTube, and the video is available on YouTube. It's now being streamed, and it will be stored over there. And I think people who want to take this exam can even just attend over there. Of course, I prefer for you to attend here and ask questions and interact with me, but it's fine if you can't, because you have other things to do and that are more important for this specific day or whatever. And in case, you can always get in touch with me offline. So I think it's not important for me. The only thing is that the exam consists in a paper presentation for 2 papers, and this is one alternative, or otherwise in a project. So the project can be done in a group of 1 to 3 people, depending on what we decide the project is. But otherwise, presentation of 2 papers is the other alternative.
Okay, thank you very much.
Any other question, either on the structure, organization of the course, or on the topics that we talked about today? I hope you have, I mean, it's not the case that you don't have questions because it was boring, but otherwise, I think we're good to go, I guess. Okay,